exciting one, and we're also going to do a really cool workshop after this, given by Ludovica Cassina. She graduated in 2020 here at the TU Delft and now works for MSc Architecture in Brussels. Yeah, so give a really big applause for Ludovica.
Hi guys, can you hear me well? Yes, welcome, very nice meeting you. I was sitting at your place only 5 years ago because I graduated from here 5 years ago. So please, let's make this informal and interactive and let's have a chat together. And I want to start the conversation by asking you guys a question. Do you agree with me that it's better to buy local food? Yes? Why? Can you throw out some ideas why you would buy like a fruit that is in season and grown locally rather than bananas that fly in or are on a ship from the other side of the world? Logistics? Yes. Yeah, reduce transport? Yes. Yeah, that could be. What? Local labor and supporting the local economy? Very good. So I completely agree with you guys. Then why don't we do the same with construction materials? Why when we go to Brico to buy a paint for a room, we never think about where it's coming from, or there's no tag, there's no nutritional properties, let's say, as we would find on food to know what's inside, and we actually have no clue where it's coming from. So this is exactly the kind of questions that I was asking myself when I was studying here. And this is what we reflect a lot on at BC. So what is BC? It stands for Brussels Cooperation, and it's actually a hybrid company made out of 3 different companies. So we have BC Materials, which is a workers' cooperative. It's literally a company that produces construction site materials and sells them on the market. Then we have BC Studies, which is a non-profit research laboratory. I'm actually here today with BC Studies, let's call it, because I'm doing education or workshops regarding the world of earth construction. And then we have BC Architects, which is a proper architectural office. We all work in the same space, we all work together, but they are very distinct, they have very distinct objectives. How did BC start? So 4 co-founders in Brussels at KU Leuven, and they got a commission from someone that they knew to build a school in Muyinga in Burundi. You probably have seen this project before. They actually traveled there, they didn't have a job, and they started checking out what was possible with the resources that were there, because the budget was quite low, and they needed to produce the materials right there on site and couldn't afford to import anything from abroad. So they started doing a lot of research and actually understood that most things over there are built with mud. They started testing it, reading online, reading books about how to transform this resource to build. And I'm going to show you guys a video that explains a bit that process. So, right after this life-changing experience for the 4 co-founders, they got back to Brussels and they started observing all around them that there's a lot of construction sites that are actually excavating in Brussels earth to make foundations, to make underground parking lots, that is just thrown away. It's brought to the landfill. These are actual pictures from the city center of Brussels. And so they started thinking, since we've had this experience in Burundi with transforming the resources into construction materials, why can we not do it in Brussels too, in Europe too? So basically, this is the main idea around which BC Materials is born. It's just to take earth that is already excavated from construction sites. To give you an idea, there's 37 million tons of excavated earth that is thrown away in Belgium every single year. And so the idea is that either when that earth is extracted, we can reuse it directly on site to transform it into a building material, or instead of going to the landfill, it's transported to BC Materials, it's placed over there, and then we have a small factory that transforms it into construction materials. This is what that small factory looks like. There are some people here, some of the students of Delft and Clay over there, who have been there to actually do workshops. It's organized in a way where big trucks just drive by and they unload all of the different resources that are excavated. This is what it looks like inside. It's also a temporary construction pavilion-like architecture, because the idea is that we have a temporary permit to actually produce materials over there, so the whole structure can be dismounted and transported somewhere else. And these are the 3 main products that BC Materials produces. I've brought some samples for you guys over there. So there are the plasters. You can see the plasters boards. There's base plasters, finished plasters, and paints. We're going to talk about that later because we're going to have a workshop on that. There are rammed earth samples and compressed earth bricks. You can go and touch them and interact with them. And so these 3 groups of materials are sold on the market. Why is this relevant? I think we all know this, but the construction industry accounts for a huge amount of carbon emissions globally. So we really have to do something different about the way we build. I'm going to take you through the project that I've been following for the last 5 years at BC. And that is kind of, I think it's a good project to represent all of the values and all of the research that we've done with the office. It's called Woodstock. This is a picture of the finished project. It's a private home for a private client who's basically told us, I want to invest some money in research in architecture. I want to do a very experimental project. We can source all of the resources locally, transfer them, and see what we can create. So the 2 main challenges of these projects are not to use concrete. We have a very, very limited amount of cement on site, only when it was really necessary, and we don't have any concrete in the foundations, for example. And we are not working with a general contractor. So the idea was also to invest in the local economy, how we've mentioned before, to really invest some money in craftsmanship and not have a big contractor managing non-specialized contractors and artisans. This is the location where the project is. We are in Wallonia, so we are around 30 minutes south of the city of Liège, if you know Belgium a bit. This is the construction site. During the construction, you can see that it's completely in the middle of the forest, and there is a river that in this picture is covered by trees over here. There used to be a building in this area. We are very close to a Natura 2000 area, so a natural reserve. And so we couldn't build new volume unless we demolished an existing house that was on this plot. Why did we have to demolish it? Because the building was full of asbestos and very unhealthy materials, and it was basically built in the 70s. It didn't have permission for everything that was built on site, so we just decided to do basically an inventory of what was there, trying to dismantle things to either resell them or recycle them on construction site. It's also a site that floods, and this building wouldn't be accessible every time that the river flooded the whole site. This is a picture of my first week of work. When I went to visit the building, it was completely flooded. And so what did we do with the projects? We decided to lift up the whole building from the ground and to change the access from the back of the hill so that the house could be accessible at all times. We also wanted to lift the house from the ground to reconnect the two Natura 2000 areas to the left and to the right of the plot, and to have kind of nature take over the site again. This is a model of the project when it was first presented to the client. And the main interesting thing about the approach of actually building this building is the kind of map that we did to decide what materials we were going to use to build it. So we basically set a radius around 50 kilometers around the construction site. And we took a lot of months of research to really map every quarry, every extraction place, every transformation facility, everywhere where they would have sawmills or produce any kind of materials, and also agricultural activity to know whether we could do something with the agricultural waste. And we arrived to the conclusion that the three families of materials that we could work with that were local were three: stone, timber, and earth. And I'm going to take you a bit through these three materials and how we've transformed them on site. We'll start with stone. The three cores of the construction are 4-story buildings built out of stone. But first of all, let's start from the foundation. So I've mentioned that there's no concrete in the foundations, which is quite crazy. There's not a lot of buildings that are built nowadays without concrete in the foundations. So how did we do it? Basically, with an engineer whom we collaborated with, we observed how streets and infrastructure is built. And it's built by using compacted gravel, as you can see from the picture. So the picture to the right is actually the construction site. We basically excavated on site until the bedrock layer that was existing there, and that we started filling up with gravel in geogrids, they're called. They're these kind of nets. They can be made out of different materials, but they are kind of like bags that collect all of the compacted gravel and keep it in place. So these sandwiches of gravel until the actual level of the construction. We then went to visit many, many different quarries around the site. Both of these were around 20 minutes drive. And then we visited this quarry, which is called GBA. It's a quarry of a very typical stone from there that had the capacity to actually produce the amount of stone that we needed for the construction, but also they had this beautiful building that was abandoned for a very long time on the site of the quarry. And the owner of the quarry, so this is myself, and this is kind of the director of the quarry, she was telling us that the family that started the quarry was actually living in it. This was their house. And now they didn't have the funding to dismantle it and to use that stone somewhere else. So we decided to really collaborate with this quarry to dismantle the house. And we said our new towers of the construction should look exactly like this, because we want to use the vernacular way of building from this specific area in Belgium. So fast forward a bit, this is the first tower, the first out of the three that was built. And you can really see a similarity in terms of construction method from the previous one. This is the start of the construction site. This was April 2022. You see the compacted gravel layer that is quite flat that we started on. And we met this group of very young masons, Addis and Pierre, who, with us, developed details and kind of the construction technique on site. This is them. We mounted this small blackboard pavilion where every week, every Friday, we met on site, we hung the drawings on, and we started sketching together to understand how to solve problems. So it was really a collaboration, and not us as architects arriving on site with finished details, giving them to them, and saying, you should execute it this way. It was really a collaboration in between us. These stone towers are built the ancient way of this specific geographical area, which means without cement in the mortar. The mortar is a mix of lime, waste from quarries, and earth. In the beginning, we also threw some hemp in there. We can talk about it further if you want afterwards. And so they are built with kind of the vernacular ways of also creating spans and openings in the facade. We had openings that couldn't be wider of 1.5 meters, because otherwise we couldn't be able to produce the lintels in stone that would actually support the masonry. Also, building with a mortar that is not cement-based, we had to arrange the construction site around a very specific planning, which is something that we are not used to anymore as builders or architects, because lime freezes in buckets. So when the temperature gets close to 0, there's no way we can work on construction site. These are pictures that I took in December of 3 years ago. It was freezing outside, and the craftsmen were like, we're not gonna go to work because there's no way we can continue to build. And so we had to interrupt in between December and February the construction site and plan around what they could do throughout the time, because it was a huge hole in their planning. This is a close-up of the masonry. We also started to play a bit with the mortar, doing some different joints. This is a picture of one of the masons who's actually building. You can see a bit the technique of how he's doing it. Here you can see a detail of a lintel in stone, and then the arches to kind of help the lintels take the load of the whole construction, because it's a load-bearing stone wall, which is insulated. So here on the left, you can see a kind of technical detail. In yellow, we have a 50 centimeters thick wall, which is then insulated with another 30 centimeters of hempcrete. And on the ground, so here, if you can see my mouse on the screen, is the compacted gravel that I was talking about. And then we needed another layer of insulation for all of the water and humidity coming from the ground. It's this one in blue. And we actually used some shells, some seashells. They're actually taken from The Hague, so from the canals on The Hague, because sometimes they just empty them to clean them from the shells. And they were also thrown away. So there is a company now that is recuperating them, washing them, and we can use them for insulation. This is a picture of stone vaults that we built from scratch. The masons were quite worried, and me too, to be honest, because they never built a stone vault from scratch by themselves. They had only restored vaults of existing churches. This is a vault from the inside. We have these chains in metal. They're covered in this picture to kind of keep the vault together. And this is the construction right at the end of the towers, when we also started mounting the wooden structure. But I'm showing you guys this picture because this huge, long building that doesn't have concrete foundations acts a bit like an airplane wing. So when there's really strong winds, it wants to lift up and fly away, which of course is a problem. So with the engineers, we studied a way to actually make the roof out of stone in order to really put some load on this roof. So this is a picture of a first prototype that we did on site. And this is the actual roof. The stones are just placed on top of the roof, and they have gravel in between them. That's it. There's nothing more to it. This is a picture as we were building the roof from the entry of the house, from the hill. This is the path to actually enter the house out of the flooding zone. And this is another picture during the construction of the access to the house via this stone bridge. Also in the interiors, we have some stone. This was a render that I made really far back to kind of show what the interiors would look like. We also started developing an idea to create a new product with the quarry, because they had saws and they had these very beautiful big stones, but they wouldn't cut them for finishing. So for the first time, we did that. So this is a picture from an interior space in the middle of construction site. And these are some tests to actually polish and use waste pieces of cut stones, very thinly sliced, for the finishing floor. So here you can see a picture of what it looks like at the end. Then we go to timber, which is the second important material of the project. It creates this portico that is elevated from the ground, as I explained earlier. But in order to study this wooden construction, we really wanted it to be dismountable and to be bolted, so that one day when the building has to be dismounted, that it would be very easy to actually unscrew the bolts and reuse all of the wooden elements. In order to do that, we created a one-to-one prototype, which is a typical way of working at BC. We build things one-to-one, we observe how they behave, and then we actually apply them on construction site. This is a picture of us building that prototype. It was actually a very good exercise because these beams on top, they completely distorted. If you go to see the prototype now, they're completely bent. And so with the engineers, we studied solutions on the prototype for it not to happen in the final building. These are some images of the bolted connections. And this is a bit the way in which the wooden part of the construction was built. So these ones that you can see here in the pictures are prefabricated cement dalles, we call them in French. So they're prefabricated elements that are just sitting in the compacted gravel foundations and anchoring these wooden elements to the foundations. And this is one of the only moments in which we actually did use cement. It was necessary. Then they built the porticos 90 degrees and they lifted them up in position. Also a picture of the construction site. This is what it felt like the first time that I walked in between these porticos. And this is a very special moment because it was the end of the timber construction site, right when nature was starting to take over the site again. This is what it looked like in the winter. You can see, I didn't explain how the house works, but basically, this is the main floor of the house. You can see that it's glazed in between the timber elements. There's all of the wet spaces in the stone towers and all of the more social spaces or bedrooms inside of this wooden boat. We also built all of the furniture and the lighting with materials from the site. So the wooden lighting fixtures that you see in these pictures to the right are made out of smoked oak. So we took some local oak and we watched YouTube videos together with an artisan and discovered that if you put oak in close contact with ammonia in a closed environment, in a closed bucket, that it actually changes the color of the oak, which we really liked to make details for the actual building. And so we created these lighting fixtures in oak, and same for all of the furniture pieces. And then we go to our last material, which is earth. There are many quarries nearby, and for them, earth is a waste because they just want to extract the stone and use it. And they always find a layer of earth on top that they just take out and bring to the landfill. So we started analyzing waste from different quarries to see which amount of clay, sand, and gravel would be in it. We wanted to use different mixes of waste to basically create two earth products for this project. A rammed earth wall, 14 meters high. I'm going to show you a picture of it later, which is very, very high, 50 centimeters rammed earth wall that you can see in its entirety. And then earth plasters for the interiors. These are some samples of the rammed earth that we did together. We did some testing to understand if this wall could actually stand up. These are, again, same samples. You can find them also over there. These are samples that we did for an exhibition to test earth plasters made out of waste and a rammed earth floor. This is a picture of that rammed earth wall that I spoke to you about before inside of one of the bathrooms. And this is a close-up of that wall. Are you all familiar with what rammed earth is? Have you seen it before? Yeah? So this is what I want to kind of end the lecture part of today with and start to think more about what we're going to do that is more hands-on. So these are samples of earth plaster that we made with different waste resources and ingredients, and all of them are possible. They are just different possibilities with different mixes, different resources that we made to choose what the interiors of the house were gonna look like. Do you guys know what an earth plaster is? Or what a plaster is? No? Someone? No? Okay, so it's in a buildup of the wall, it's usually the last layer of the wall. It protects what is structural inside of the wall. Historically, it was made out of what was available in a certain environment, often clay or lime for renders for exteriors. And do you have any clue what an earth plaster is made of? What the ingredients are? Yeah. What? Marble? Limestone? That is true for lime stabilized earth plasters. So when you want to use them for an exterior, you do add lime or marble powder. But in reality, a pure earth plaster has no lime in it. Do you have any other ideas what there could be inside? Clay. There is clay. And then there is another very important resource that is inside. Loam? Yes. And then a third one? Yes, but sand is the third very important one. Then you do add water to actually make a plaster. So this is a granulometry if we were to look at these ingredients. So we said clay, silt, which is a very fine sand, and what we call loam, which I heard someone say, is a mix of clay and silts. And then we have sand, which is a bigger granulometry of silt. And what is the difference between these different ingredients? If we were to look them at the microscopic level, they work completely differently. So this is a sand particle. It's a sphere. And then we have clay particles, which are actually small, flat particles. This means that these two different materials, clay and sand, they behave in a very different way and they have different properties. We all had the experience as kids to build a sand castle. And we know that when sand is wet, we can build a nice castle on the beach. But once water content is out, the kind of binding between these particles falls apart. And so the sand castle falls back to pieces. Clay works very differently. Clay is a binder, and it works a bit in the same way as dishes do when you take them out of the dishwasher and you put them on top of each other. There's a small layer of water, and they tend to stick to each other. You cannot take them apart anymore. Sometimes it also happens with glasses. And so when water goes in between two plates, these two plates start sticking to each other. And this is why we considered clay the glue of an earth plaster, and why we consider sand the structure of an earth plaster. So we need a mix of both to be able to do an earth plaster. Potentially, we can also use fibers and different kinds of materials to give different properties to our plasters. These are some pictures of the actual products that we produce at BC. So on the top, you see the ones with the biggest granulometry. They are base plasters. Then we have finished plasters, which are finer. And we also started producing paints that you really applied with a brush that are also based off the same resources. In order to explain to people what they feel like, what they look like, and for them to touch them, we make samples. So you can see them over there. You can see the different colors. And yeah, if you want, you can also pass them around. And these are very useful, also to do testing, to understand the behavior of a certain recipe that we want to test. And it's also what we're going to do later today together during the workshop. At our factory, this is the way that they are packed in bags in order for them to be sold to the public. And this is a typical wall build-up. So generally, when you have a wall that is finished, you need a rough surface to be able to apply base coat of earth plaster. So if the wall is not rough, we make it rough in different ways, and then we apply base coat. We then need, and I'm going to show you a picture later, sometimes reinforcement mesh. There are nets that we use to allow the plaster to be flexible, especially when we have doors or lintels or openings, so that it doesn't crack. Then we generally apply a finishing plaster, and then we do surface treatment. So on construction site, this is the way that an earth plaster is gonna look like. It's gonna be mixed in big quantities. We're gonna apply the base. As you can see here, there's a very rough base. These are the meshes that I was talking to you about. They are used, for example, here there is an opening, and so we need to give the material more flexibility so that it can move freely. This can be made out of different materials. The one that we also started producing at BC is made out of flax natural fibers. We let the plaster dry, and then we apply our top coat, which is generally thinner than the base coat, and it's what we're gonna see in our rooms. And it's also what we're gonna produce today together, a finish coat that is much, much thinner. At the end, when the plaster starts drying, we treat it with a sponge to remove the top dust particles and to really smoothen the surface. And this whole buildup or material starts to really have beneficial properties in a room because it has the ability, a hygrometrical ability. So it's able to absorb humidity and water and release it in the environment when the air is very dry. But it's also a material that, of course, can have different colors depending on the resources that we're using. But we can also fix it constantly. So if there is a crack or if we break a part of it, we can just re-wet it and correct the mistake by just reapplying the material. And the other thing is that because we are not changing the physical properties of the material, we're not baking it, we are not doing anything to it, that is really earth on a wall. So if we want to take out that plaster, we can just scrape it off, and it's just sand and clay that we can either throw in a garden or reuse for something else. So now let's start to discuss a bit the workshop and how we're gonna do it. The objective that you guys have today is to tell us in a group what you think is the recipe of an earth plaster. So I gave you the main info about what is in the mix. You're gonna have the resources and touch them with your hands. You're gonna make different recipes, and then this afternoon with your group you're gonna tell us, we think that if we were to sell this material, we would actually go for this recipe. So you're starting your own material production company. And at the end of the day, the idea is to have a lot of different samples that we can compare between each other. They're gonna have different properties, different colors, different resources. And we're gonna have them all in an exhibition. So how is this gonna work? We're gonna divide, you guys are 80 people. We're gonna divide you in 8 groups of 10 people. They're divided by color. And each group needs to make 5 different recipes. You can also keep experimenting if you're done early. You can really play today. It's a space to play with the resources. So for example, if we take the yellow group, their ingredients are yellow clay and sand. And they're gonna make 5 samples. The first one has a recipe 1 part clay to 1 part sand, all the way to 1 part clay, 5 parts sand. We work with volume, not with weight. So you're gonna have cups to measure resources, and you're gonna divide a certain volume to respect this recipe. It's a bit like cooking, so take it in this way. If you mess up, there's no problem, because we can just throw away the material on the ground. If we zoom into the yellow group again, you're gonna work in couples. So 2 of you are gonna work on a specific recipe. And the idea is that you produce one final beautiful sample that is gonna be part of our exhibition and that we're gonna compare. As a group of 10 people, you're gonna have some tools. So you're gonna have a bucket of water, different trowels that you can use, sponge. And then for every couple, you're gonna have a mixing bowl, a measuring cup, a spoon to mix in your bowl, trowel, and 2 tablets. We're going to show you outside that there are 2 tablets prepared per couple. You have a smaller one that is just for playing and testing. So I would recommend you to start with this one. And then you have a square one that is going to be the final exhibition tablet. So once you're confident with the mix and you feel like you know the recipe and you know how to apply the material, you can transfer it to the bigger tablet. How is this going to work? So we are going to divide you in groups. You have this paper printed, so you can always read it later. But basically, you're going to first calculate the volume of resources that you need to create your recipe. You don't need a lot of resources, so start with very small quantities, and you can always increase the amount that you're producing. So start with an overall volume of 100 millimeters. Example, if you have a recipe of 1 part clay to 1 part sand, you take 50 milliliters of sand and 50 milliliters of clay. It's quite straightforward. It's important that whenever you work on a tablet today, that you always write your recipe on the back. So we have some paper tape and pens. You just note your recipe, because at the end of the day, we're going to have 40 final samples. And when we want to compare them, we always want to be able to turn them and read what you actually did, because you think you're not going to forget, but you are going to forget for sure. Then you can go to the bag of resources. So outside, we've prepared some big bags. You can read what's in them. And in your ingredients on the previous page that you're going to find outside, you're going to find your ingredients. So you just go to take the actual ingredients you're going to use. You add the correct amount of water to the mix. So this is really important. And I've prepared a mix that I want to pass around now so that you can touch or see it, and you know how much water you're actually going to need to put in. I'm going to start here, and you can pass it around. So it's not very wet. It's not a lot of water. If you mess up and you put too much water in it, no problem. You just add other resources to give it a good texture. Then you transfer this on your sample, and you start working with the material. You're going to have different kinds of trowels. You have painter tools, you have plastic trowels, you have real construction site trowels. So just, test them, experiment, see what you feel comfortable with, and you start playing with the material. It's important that you respect a thickness of around 2 millimeters. We actually want our samples to dry today, so that in the afternoon we can sponge them and they can be exhibited. So if you work with much thicker plasters, they're not going to dry in time. So try to stick to 2 millimeters. And then this afternoon, we're going to sponge them. We are going to start our exhibition, and every group is going to present what they think the right recipe is. We're going to have a final reflection about what we did today. Is that okay for you? Is it clear? Yeah? Wait. Is there a? Of what? Water. You just have to observe what I did and try to reproduce it. So I'm not going to give you the amount of water. It doesn't have to be liquid. You'll see when you touch that bowl. I don't know where it is now. But when you touch it, you're going to feel the material, and you're just going to work with your hands until you reproduce something that is more or less similar. So there are no pigments that we're going to use today. We're just going to use clay, which is actually a pigment. It has color characteristics. So I didn't mention this, but in every earth product, what gives the color to the material is the color of the clay. So we're all going to use sand that is excavated from Brussels. It's a yellow sand. This is not going to change the color of what we do at all. It's just our clay. So we're going to have red, yellow, white, and gray clay. And each group is going to focus on a color, and that's how it's going to go. So there's no additional pigments in the mix. Exactly, yeah. They're all natural. 3 of them are from Belgium, and 1 of them is from Germany. of the ones that we have today. But in general, when you see earth construction around the world, the color of it is given by what kind of local clay there is over there. And it changes. Generally, clay and sand you can find anywhere. They all have different characteristics. So that's also why it's interesting today to test, because one group using white clay might not have the same result necessarily as a group that uses red clay. More or less, we have a basic rule ratio that we always start with. I'm not going to tell you what it is. You're going to tell me at the end of today. But it really depends on the kinds of resources that you're going to use. So we'll see. Also, some of the recipes are really wrong. So you're going to see them cracking or behaving weirdly. That's also a bit what we're going to discover today. Keep in mind that if you use too much water, it's also going to crack most likely. So we can also play with that. You have many more tablets to experiment with at the end. So if you do your mix in time and you have your final tablet, you can also start playing with all of the resources that we have available outside to test also different kinds of recipes. Anyone has other questions? Also on the presentation or on the project that I spoke to you about? Yeah. Oh, it was so long. It started in 2022 and it finished last week. Yes, the building materials and the kind of craftsman group that we worked with. So we were not only the architects, but also the construction site managers of the project. So we had to make the planning for the contractors, which meant that for us, things had to happen. We need the planning to match with the craftsman planning for other construction sites. But mainly it was also because of the building method and drying times of the materials, and because in very cold months we couldn't work on site. Yeah. Yeah. So, yeah. Yeah. I think this project was really about experimentation. So kind of setting a precedent and experimenting with recipes so that we can have them written. I actually wrote a full kind of diary or book of the construction site that reports all of the mistakes that we did and all of the recipes that we tested. This is something that we can share with other people so that they can just start from our final results. It also took a lot of time because we started with zero knowledge about this specific area and what we could do with the resources existing. So I think some of them are really replicable. For example, the insulation types that we used, I spoke about hempcrete in the stone walls, but for the wooden structure, we used recycled grass fiber insulation. The interior finishing are very easy to replicate. The only expensive things about earth-based product is that labor can be a bit more intensive, although for plasters it's not necessarily the case. We are really fighting to also form existing contractors so that they can start applying this material because it's basically the same procedure. So I think there are things that are too experimental. For example, the foundations, it's not something that you can apply to any other construction site in this area. I mean, it was super expensive and super difficult to do, but it was interesting to test it, to have enough budget for this very special project to say, let's see what it actually takes to not use concrete for a foundation. So I think it's a balance in between things we've learned and that we can replicate and things that we cannot replicate. Other questions? Yeah. Yeah. Yes, you can drill into it. Yeah. No, no, no. It's really how we built until a few centuries ago. Everything was built with this kind of material, especially in the interiors. But no, we have plenty of projects where the interiors are completely done with a clay plaster. It's quite resistant. Also, if you touch it, I mean, you can feel that it's not that it's crumbling. It really feels like a wall. So no, it is resistant enough. Yeah. Hi. Yeah. Yeah. Actually, there are almost all of the projects at BC are public projects. So this is really an exception. And it's way trickier in those situations to really fight for this kind of experimentation. At the same time, we really feel that the public is becoming more and more interested, and policies are more and more going towards more sustainable materials. So people start to really contact us because they know we have this reputation that we can make this happen. So it's a bit easier in that sense because it's not that we are starting as a typical architecture office that does concrete construction and then we say, oh, let's make it in earth. So people really look for us for that. I think there's a lot of possibilities with urban sourcing, with reuse in public projects, for example, which is not necessarily related to laboratory experimentation to create materials, but to transform what we already have over there. So there is a project in Brussels called U Square. I don't know if some of you have heard or seen it already, but it's a project of a university, a part of a university campus, where we did dorms for PhD students and researchers and also communal spaces. And there we worked a lot with reusing all of the stone that was present in the existing buildings, dismantling bricks that were in the construction to clean them and reuse them for the new construction, which was really, really a difficult process because contractors are not used to demolition that takes care of actually dismantling the blocks to be able to reuse them. So actually for them it's cheaper to destroy the wall and buy them new. It's also a matter of education and working with contractors to make a point on how we should do things. Often when we, for example, win a competition like the one of U Square, it's stated on the cahier de charge. It's like the, I don't know how to say it in English, but it's basically the booklet where the architect prepares and writes down all of the prescriptions for the construction site. And there we stated that all of the bricks needed to be dismantled in a certain way, explaining the process, cleaned and reused for the construction. So it was kind of a legal document that we used to say it needs to be done this way. There was a lot of experimentation on public projects also with workshops. So a lot of it because the client was like, yeah, we're not gonna pay extra to hire very specialized contractors that are gonna do hempcrete interiors. Then we're gonna organize a workshop with the universities and with the students to actually build that together and make a point that it's really possible and it's not that difficult to build with this material, for example. Other times it was about finding what the client really wanted. For example, another thing about this U Square project, they really wanted to put expensive acoustic panels on the roof of meeting rooms for PhD students. And we said, we think we can develop a plaster that is very rough with waste from flowers that is inside and that is gonna give really good performance in the space. And they said, okay, if you want to test it, it sounds cool. We can publish an article about it and go ahead and test it. And it worked really well, finally. So there is some opening for experimentation. Of course, it's way harder, but it's doable, at least in Brussels. I think in the Netherlands, it works a bit differently. So I don't know if it's necessarily possible. Yeah. Other questions? Yeah. Mm-hmm. Yeah, yeah. So, as a principle, sand is our structure and clay is our binder. if we were able to replace our structure with something else, the mix could work. So one experiment that you are going to try today is to use fibers instead of sand in some of the mixes and see how that behaves. But for earth construction in general, we're highly dependent on sand. So in a place like Brussels, where this material is abundant in the geological stratification of the soil, it's of course easy to do that, but indeed that's not the case everywhere. So there's different techniques in earth construction depending on where you are in the world that developed in the history of the vernacular construction methods of that place, and that is often related to the fact that there used to be sand or not, there used to be a kind of clay or not, there used to be fibers or not, and yeah. Yeah. Okay, cool. Yeah. 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 Yeah, yeah. So for us, the starting point was this 50-kilometer radius around the site. You soon realize that it's not possible to be so strict on that, on many aspects of the construction. The seashells part was a material that we could have easily replaced with a more local option, but we really wanted to try this waste material to implement it in a project because it seemed very interesting. It's completely a waste, so we thought it's not that far away. It's around a 3-hour drive. Let's try to implement it in a project and see how it works. So it was an exception, but we also did other exceptions on site. For example, I mean, taps or pipes, these things, it's unless you have someone who produces steel taps around the corner, you're gonna have to import them from somewhere. And then I remember at that moment, I was really thinking like, what is a sustainable tap? Or what is the most sustainable tap that we can find? It was a difficult question, and then I started Googling and searching different manufacturers to see if there would be any differences in production. And in the end, because nothing was produced locally anyway, I found this company in Denmark that is producing, that doesn't have collections of taps, because that's another problem, that when a tap breaks in 20 years, 30 years, that you don't have the change pieces to actually fix it, and you need to throw it away and have a new one. So I chose this company, which is not local at all, just because they didn't have collections. They've been producing for the last 50 years the same exact model that is made of full metallic elements. They're either copper or steel. And they, yeah, with the idea that we could always fix it for the lifespan of the house. So I think drawing the limit is very, very difficult. You can try to make a rule for yourself and say, I'm gonna try as much as I can to push to actually do this within a range of 50 kilometers. But I also need to be open for compromises, otherwise it will never work fully for a finished project. Yeah. The house doesn't fly away, yeah. No, they're heavy enough. I was also scared of that. The engineer told me, no, there's no way they're flying away. They're big stones, 6 to 8 centimeters thick, very, very heavy. So he's sure that they're not gonna fly away, I hope. Other questions? Yeah. Yeah. Yeah, so I think there's like the question is really interesting overall, and something that I want to add to it is places used to have vernacular knowledge and know how to actually build with natural materials or in vernacular techniques, but these people don't exist anymore. I'm from Italy, and in Italy we used to have many specialized craftsmen in different techniques. You cannot find them. And if you go in villages, there's maybe one 80-year-old artisan who still has the knowledge, but no one is interested in it, so he's just gonna die and not pass the knowledge. So I think something that we are really trying to push as BC is formation and exchange between craftsmen. In this project, all of the earth construction is not done by local artisans, I mean local really from that village, while timber and the stone part are, because there's no transferred knowledge through time. So there was a craftsman from Flanders who actually came there to teach some locals how to work with their local resources and how to transform them into materials. So I think it's super important, if we want to work in this kind of way with this approach, to be aware that we are not gonna find a lot of people who know how to do it. And we need to also weave networks in between all of the steps of the chain that is needed to actually build a building. So it's engineers who are open to calculate a load-bearing stone construction of 4 stories, which no one is building anymore, contractors, specialized craftsmen. We need to create a team of people that is able to do that. And that often means creating workshops or instances where people can learn from each other. Someone can travel maybe for a week to teach a certain craft, and people can keep doing that. Of course, that is also related to supply and demand. It's also the reason why these materials are now expensive on the market. The more we create demand for it, as architects, as material manufacturers, but also we really need change from the top, like policies that start saying that the carbon emissions need to be cut on construction site, et cetera, et cetera. And then I think the answer is just weaving these networks of knowledge and allowing for people to learn from each other, because there are some techniques that are not vernacular in a certain place, but and the resources are there, so they could use it, and it could become something that is locally done. I don't know if that answers your question, maybe partially. Yeah, local resources and local construction, but not necessarily local knowledge. It's my point of view on the topic. There was a question? Yeah.
I'm sorry. Okay,
sorry.
it will be the last question because
okay.
we have to go to the workshop.
Okay.
Perfect. Yeah.
It was done in stone. It was always cyclopean foundations with big stones, or most often in this area, because there is a bedrock layer. Here we're very close to a river, so there's quite a thick amount of earth in between the construction and the bedrock. But all of the villages are built uphill, and so the stone is really, really close to the foundation, so they would just remove the soil, flatten a bit the stone, and then that would be their foundations. Okay, sorry, too many questions.
No, that's okay. Okay, thank you so much. Yeah. So right now, Flora is going to connect her laptop to the screen, and she will show the groups on there. It's not working. Ik denk jij gewoon die eruit moet halen.